This is Mike Sayers. I'll be making the presentation. I'll be going over the new features in uh, our vehicle dynamics products, CarSim, TruckSim, and BikeSim. It was released December 18th. I'll be covering 5 topics, although I got to admit that the fifth one is going to take about half of the time. But we have improvements in our overall architecture, the animation database management, improvements in the vehicle models, improvements in the way we connect with other tools, and lots of examples in the fields of ADAS and autonomous vehicles. But the first thing, which is not really a software update, but it's the way we do business, is our company has grown a lot in the last few years. So I want to just mention that because that pertains to how you interact with us. The picture in the upper right here is 20 years old. That little kid on the left there is Dr. Yukio Watanabe. The kid on the right is Dr. Jin Hu. The guy with hair in the middle is me. Now we have a picture below here. We have 30-some people, 34 I think, plus a few part-timers. In the last 3 years, we've increased our staff by 144%. We have a lot of disciplines in our technical development. We have mechanical engineers, software engineers, computer engineers, and a team of artists. You'll see the effects of those in a minute. One of the things that we have that we didn't a few years ago is online support center, so that instead of just emailing Ben or Jen with a question, it goes onto our tech support thing. It goes into a database so we can track the trends in what problems people are having or what features need to be added, and we can follow up, and we have options for users in the same company sharing information and so on. With our new capabilities, we've increased our release cycle to make it a lot more steady than it used to be. We're now on a schedule where we make 2 major releases per year, December and June. We almost did it with the 2017 release, but we had some bugs to fix, so there was an early release for May. But in 2018, we were on target. We released 2019.0 on target in December. So we're doing this on all platforms. Oh, and by the way, with our past ones, it was just the vehicle dynamics. Now we've added suspension sim to the process, so we should be seeing regular 6-month updates for suspension sim as well. We run on Windows, 2 Linux platforms, and 8 real-time systems. We also have desktop driving simulators and a few other oddities. They're all released at the same time. To do this, we use automation, lots of it. We have a room back here with stacks of computers that are running 24 hours a day. So the result is that if one of us submits a change in a tire model involving C code, as soon as it's submitted, about 10 minutes after that, it's available for testing by everyone in the company. And a few hours later, it's even available on the RT systems. We do continuous deployment for the software that we write, the database, so the same thing applies with our mechanical engineers who are making fixes to examples or adding things. And nightly, we do new installers. We also test the reliability of new the new versions with automated smoke tests. Now, on the slide here, on the left is the rack of computers. On the right is a photo taken a couple months ago in her office. This is Kathy, receptionist and office manager at her desk. The monitor on the left is showing a bunch of tasks that are things being compiled and built. The one on the right is showing things being tested. This is already a little obsolete. We have 2 more monitors that are being installed right now. Green is good, red is bad, and you want us to see the red so things will work when you get it. Every night, we also do performance benchmarks, where about 10 example simulations are each run 1,000 times, and they're timed. Windows is not a real consistent system, so we don't get the same timing every time, but we can get a max and a min and standard deviations. This plot here is a report that I received a couple months ago, and as you go left to right, each one is a different day. Okay, we've made many minor improvements in our architecture, things like the database and the animator and so on. Some of those I'll be showing later on in the ADAS examples, but I've got a couple slides here that are substantial and worthy of just being discussed by themselves. A year ago, we added capabilities for running with Python, and in this release, we've improved it quite a bit so that in addition to using VS commands within the solver when it's running, you can run Python. We have, when you're running on Windows, it's available as part of our installation, and it's, in addition to the VS commands, we'll let you add equations and define new output variables and so on. Python gives you function calls, looping, access to libraries that are done in other languages. I'll be showing later some examples using TensorFlow. And the improvement is that we have access to all the VS Solver variables and all the tables. It's completely installed in 19.0 in Windows, and it's supported in Linux. We had a last minute glitch, so if you want to run Python within the Linux version, you can call us and we can give you the details of what you have to download, but the hooks are all in the solvers to support that. Part of our packages are animations. We started out with wireframe animation when the company started. Then we had SurfAnim, which had surface animations. About 5 or 6 years ago, we switched to VS Visualizer, and we've dropped support for the old ones, which means we can now use new files that are much better. They're smaller, so we can put more of them in the system, and they look better and support advanced reflections and lightings. We've reorganized the way we provide these assets so that anything that we provide in CarSim, BikeSim, or TruckSim is now available in all three products. We also have done some driving simulators, and some of the art assets that we use for the driving simulators are also included in here. So you have trees and bushes and fences and bus stops and buildings, things like that. Now, next topic, vehicle model improvements. We've been doing this a while now, and there are two big complaints that you users have about our software. The first one is that it's too complicated. All those parameters, thousands of outputs, nobody understands the whole thing. Can't we make it simpler? And the second problem, except for whatever my interest is, my specialty. In that case, it needs to be more comprehensive. Can't you add more detail? So these conflict a little bit. Just so you know, our approach is that we make system-level models. Our goal is to have the model reproduce results that you would measure in the field in terms of getting the vehicle motions in response to what a driver does with steering, shifting, braking, gears, throttle. They're parametric models, so it's easy to do variabilities and sensitivities. They have to run fast. We support all these real-time platforms, and typically CarSim model will be 15, sometimes even 20 times faster than real-time. But because we don't have the detail that you want in your specialty, we have many means for extending the models, which I'll get to later. Our models are thorough. We have all the 3D connections for the suspensions and using rigid bodies, brake systems with lots of options, steering. I think we have 8 combinations of model options for the steering system. Our built-in tire model is pretty thorough. Plus, you'll see that we support many external ones. We have powertrain, aerodynamics. And something that we introduced a year ago is modularity in CarSim and TruckSim. That's opened up a lot of opportunities that we're starting to show off here. Now, when we introduced CarSim 18.0, CarSim, as you may know, supports trailers. You had in our GUI a choice of a trailer with one solid axle or a trailer with two solid axles. Our solvers actually supported a lot more options when we became modular. We now just have one CarSim DLL that plugs in, and then you pick and choose which options you have. In 18.0, you could do a 3-axle trailer, but it was hard. Now it's easy. We're looking at the trailer screen up here. So this is a new screen that supports 3 axles. They can be any combination of solid or independent. In TruckSim, there's almost endless opportunities. These are some examples that I showed almost a year ago. In TruckSim, the top one is a guy with 9 axles. There's a tridem and three tandem suspensions in there. The one on the bottom has a tractor towing 16 semi-trailers, combinations of dollies and semi-trailers. We support these. They run, and surprisingly, they run pretty fast. Both of those models run about 2 times faster than real time on a Windows machine. Now here's a summary of what these modules are. On the right, under type here, we have 4 types. One is the lead unit sprung mass. Second is a semi-trailer sprung mass. The third is suspension with steered wheels that's connected to a sprung mass. And the last is the same thing, but the wheels are not steered. We provide that option because when we get to the big TruckSim models, having suspensions where the wheels are not steered means a lot less calculations and the models run faster. So to go through these quickly, for CarSim, for the lead unit, we have a basic one that is 6 degrees of freedom. We have that plus a mounted engine that has 6 degrees of freedom to get realistic interactions between the engine torques and the sprung mass and some vibrations. And we have a frame twist that's in there with rails on the left and right that you need to get accurate reproduction of sport vehicles, open wheel race cars. In TruckSim, we've got the basic one plus the frame twist, which is necessary because heavy truck frames are not rigid. And the one with frame twist also has a suspended cab. For the semi-trailers, they're either rigid or with frame twist. And then each kind of sprung mass needs the connections to the suspensions are different. So we have to have a solid axle steered for the simple one, solid axle steered to go with rails. We've added a new option in 2019.0, Dynamic X Motion, that I'll talk about in the next slide. When we went to this modular concept in 2018.0, we were trying to address the need to have a more accurate or more representative model for twist beam suspensions. And there was a working group with 4 Japanese OEMs that Dr. Watanabe from Mechanical Simulation was part of that. So the change is basically that we extended our old independent suspension model so that instead of having 1D functions in there like toe versus jounce and camber versus jounce, we made them 2D functions. So it's toe versus jounce on this side, and then possibly another independent variable would be jounce on the other side. If you don't have the data for that, they revert to 1D tables like we've always had. But now they're 2D tables, so we can get some interactions that quite easily just taking the KNC data that's generated routinely. And if you don't have KNC data, you can use something like Suspension Sim or Atoms to do the detailed model and replicate the KNC tests. The result after a year of using this has been real positive from the members of the working group. They're finding good agreement between the proving ground results and the CarSim results. New for 2019.0 is a degree of freedom that some of you asked for that has not just vertical dynamics but also longitudinal dynamics. And this goes into ride applications. So it's a generic suspension where if you hit a bump, the longitudinal deflection is not quasi-static, it's actual dynamic. It's got the mass, and we have nonlinear stiffness and I think nonlinear damping in there that will give it true dynamics. So we're not really sure how effective that is. We'll be looking for feedback from those of you who want that, who can exercise that feature. Here's a summary of some other new features. I'll be covering the first 2 in more detail, but besides the So going to the third one, we've made some improvements in our speed controller that it more accurately does what you want it to do. Some minor improvements in the tire models, brakes, powertrain. When it comes to ADAS applications, I'll be talking about all the paths and roads that you can have. So we've increased the number there so we can have 200 paths and 100 roads. We have a feature for linearizing the model, generating A, B, C matrices that can go into MATLAB. And we also support a restart thing where you can jump back in time and continue. As the models have gotten more complicated, there are some edge cases that these didn't work properly, and that's been completely redone for CarSim and TruckSim, and will be done for BikeSim in the future releases. Okay, the hybrid powertrain. This is where we are using an internal combustion engine and an electric motor with a battery and a generator and a planetary gear set to connect them. In 18.1, we shipped CarSim with a Simulink example right here that we're looking at. This was generated by researchers at the University of Michigan and validated using some test data they had. We took it and cleaned it up, made it a little bit robust for handling cases like being stopped and some rapid changes. As you can see, it's a complicated model, but it matches. It's kind of a Prius style of sharing the resources. It has a controller over here, internal combustion engine, generator, electric motor, battery, and a planetary gear that connects them. And then this is the CarSim guy down here. Now the good news is it works. The bad news is it's kind of slow. Here's a log file for that run that was made in Simulink. So this is running an EPA cycle. It's 1369 seconds long. So 1200 seconds would be 20 minutes. So this is 20 some minutes. It runs a little more than 2 times faster than real time. So that means that if you run this on my machine, it's going to take about 10 minutes to complete. Now what we've done for the 19.0 is take those equations, the model, and build them in. So now we've got the engine electric. So here's the engine model. It's just like we've always had. And here's the powertrain assembly. So we have the battery, the engine, generator, motor, planetary gear, some parameters involving the planetary gear, and just summary information, and then lots of tables that have nonlinear relationships. If we go up and that's the assembly. The power management also is built in. It has a new screen that's basically telling whether the internal combustion engine should be powering the wheels or recharging the battery or maybe turned off. And this also has just lots of tables in here. Or not a lot, 2 tables. So how does it work? Well, first the efficiency. This time now instead of running 5 times faster than real time, we're going 10 times faster than real time. I'm sorry, instead of twice. So it's 5 times faster. Simulink was really slowing it down. This means our 20-some urban cycle simulation is going to be done in about 2 minutes. And these are the kinds of results that we get. This is the cycle up here as the speed is going over that period of 20 minutes. Then we're getting information about the battery and the efficiency, fuel consumption, things that you're interested in if you're using a hybrid simulation. Okay, the next topic, the next improvement is to build in electronic stability control. We've had examples doing this with VS commands. Now, since they've been required by law for cars since 2012 and in trucks for just a few years, we're putting this in. It's a simplified version that's similar to our ABS controller for brakes. So here's an example in TruckSim. This is a simulation of a truck making a step steer. The steering angle just goes up as a step, and there's a slight instability. Watch carefully and see if you can see it. Yeah, that's it. So now we'll look at it with the controller on. Okay, we see the icon, the stability heads-up display coming, and it goes through the maneuver without rolling over. That's good. We got the controller algorithm from one of our customers, a truck company, to use in a driving simulator. So it's been cleaned up, so it's fairly generic and easy to apply in different applications. It's predicting what the yaw rate and the lateral acceleration will be. So you can see here that when the predicted yaw rate, which is in blue, is small, it's off. When it climbs up, the controller kicks in. That was the um, angular velocity. Here's a similar thing for lateral acceleration. And then this is the braking that is applied. So now that the controller is in there and it's selectively triggering the brakes to keep it to reduce the acceleration. It's lowering the speed quite a bit. Let's see, where's my speed? Ah, yeah, here we go. Yeah, so the result of this is that it does slow down because that's kind of the only surefire way to stop the rollover. Now in CarSim, it's often used for things like sign with dwell testing. I want to show a sequence of sign with dwell tests that's done for, oops, I need to go to that data set. That is miscellaneous. Here we go, sign with dwell. The first thing you do is you steer the, you ramp up the steering wheel angle linearly until you reach 0.3 Gs, and then you reset and go the other direction until you hit 0.3 Gs. In making this simulation, we turn writing to the file off during the transients between sequential tests here, so you don't see the uninteresting parts. We just see when it's doing the tests. And then it gives it this sign with dwell waveform that increases as you go along until a limit is reached, and then you do it with the opposite sign. We're looking for results like this where it remains stable and controllable the whole time. When we look at the controller, it only has 3, 6, 10 parameters here. One parameter is a vehicle understeer gradient. That's what it uses internally to predict what the response is going to be. So let's go back at these plots here, and we'll look at, say, this is the angular velocity as a function of time for those tests. Red is what it really is. Blue is what the controller thinks it will be. And it's right on for the early stuff. And the reason that we're able to match it pretty closely is because one of the output variables is the understeer gradient as calculated for the assumptions of that controller. So I'll zoom in and look at this. Show the values up there, and you can see 3.23, 3.189, and then we go back and see that the parameter that was put in here was 3.19. So it's mainly doing a test like this, you can see what the understeer gradient is and put it in there. So it's very easy to tune this controller to your vehicle. Same things it's the same controller in CarSim and TruckSim. Okay, connecting to other tools. Next topic. This is how we address the problem that when it comes to your specialty, we're not detailed enough. You need to extend it. So we have over 100 technology partners that we're sharing information with. These are some of them. Here's a set of the partners that we give direct support to. We have changed our software to work with the tools from these companies. You're all familiar that we have MATLAB and Simulink support, also LabVIEW and EDOS ASCII as external workspaces. Over on the right here, there's a kind of an open source, open standard called Functional Mockup Interface that we support. They have versions 1 and 2. We support both. Flat and structured I/O definitions. We do both. 32-bit and 64-bit. Now the way we connect in MATLAB, LabVIEW, and ETOS is that the solver runs in that environment, but it's getting data from one of our standard databases. So if it's CarSim, you would have the CarSim database installed. If you're, say, in Simulink, you're running under Simulink, but it's getting data from the CarSim database. With the FMI, we support that also. But with FMI, we also have the option of making a standalone unit that's completely self-contained. So that has all the vehicle properties, anything that's specified from the database. You make that FMU and you give it to a colleague on a different computer that doesn't even have CarSim installed. They can run it in their environment. Now they can't change anything. So it's mainly useful for control engineers who view the car as a black box and just has inputs and outputs. We run on 8 real-time systems that are listed here. We support a lot of third-party tire models. Okay, when it comes to what we run with, up here in the help menu in our release notes, we have system requirements. This is the document that you get, and here are a lot of the real-time systems. This table lists most of the tire models. Some of them, they're all available on Windows. Some are available on DSpace and some are available on Concurrent. It depends what version. It also depends which of our products, CarSim, TruckSim, or BikeSim. We have information in this document about all the real-time systems that we test. We try to be up to date with the current releases, although very often if there's a new release from DSpace and they've changed things, you might have to wait till our next release so we can implement those. But I think we're pretty much caught up now. This year we've added support for the Michelin Tame tire, and we have taken what used to be the CarSim plugin for EPIC Unreal and made a Vehicle Sim Dynamics plugin, and I'll be showing that later. Connecting to outside software, we have lots of application program interfaces, APIs. We plan in the next year to the next few months to make a bundle with these to make it easier for programmers to have a SDK, a software development kit, but they exist right now. And are in wide use. The Solver API lets you run our solver from external software. That's used in driving simulators and some optimization things. A few years ago, we standardized the way we connect with tires. There's an old standard called SDI that was made for Fortran maybe 30 years ago. We've taken our own version of it that's compatible with C function calling protocols. That's what we use for most of the tire interfaces, and it's been used by some of you OEMs to connect your own tire models into CarSim and TruckSim. A few years ago, we had an API for communicating with our visualizer so that you could see a camera that it is installing as if it were a sensor, an onboard camera. Everything it sees is available to outside software using that API. We have a couple new ones for dealing with our output files and nonlinear tables. There's one that I'll be showing later, VS Connect, that allows two programs that neither one will plug into the other. They have to co-simulate. CarSim can plug into one and Connect API plugs into the other. And new in this release is the Train API that lets you make use of ground information from outside sources in a generic way so that you can connect your own ground to our stuff without us knowing about it. Okay, now The rest of the presentation are examples in the area of ADAS and autonomous vehicles. But before I can show anything, I feel compelled to give a quick review of the ways that we describe these things. Our vehicle models are based on physics. The physics equations all use global x, y, z coordinates, yaw, pitch, roll, angles for orientation. When we're talking about traffic and intersections, it's more convenient to use path coordinate systems. So if we have a path, the coordinates are station S, where you are along it, and L, lateral distance from it. You'll see this with some European um, technical papers. They'll call them S and T, but we use T for time, and we're not going to give that up, so we use S and L. This is real good for defining movements of traffic vehicles. It's necessary for defining roads. We've used it for 20 years for our driver model, more recently for the moving objects and lane edges. And a lot of making ADAS scenarios involves setting up paths and connecting roads. Now here's an example this was made in our previous release. Notice we have walking pedestrians that are moving. Events are being used down here to stop the car, wait for the pedestrians and the bicycle to clear it, and then speed up. Now I want to show a few other things, so I'm going to kill that and go live again. Okay, we'll look at the same example here, and I want to talk through it a little bit more. So we see that we have two pedestrians waiting here. Neither of them are moving. They're both showing realistically standing. They're not like walking and frozen. Now the woman starts walking. The guy starts walking just a little bit after she did. They're walking at different rates. He's going to catch up with her. As they're walking, their feet touch the ground and stick to it. They're not doing any Michael Jackson moonwalk kinds of move. They're maintaining that realistic motion. When the bicyclist comes around and she turns, she's leaning into the turn. The lean is physically correct. It's v squared over r is the lateral acceleration divided by g. Take the arctangent of that and you get the lean angle. The other biker keeps going straight. When everything is cleared, we go past the through the intersection. We see the blue beam connecting with a speed limit sign up there, so it's changing the speed used by the controller in the car. Now it detects the bike, and you see that it's going to give her some respect here, moving to the left to give some clearance. So the way we do that is with a new feature or that simplifies that. When we have our events now, there is a group ID that you can check. And this is the ID is bike lane. The condition here is saying that if our speed is more than 5 meters per second and our closest object is a pedestrian and the pedestrian is closer than we want them to be, then we will go here and change the target that we're using to drive, and this is updated every time step. It will move it to the left. We'll keep doing that until the type of the closest object is no longer pedestrian. Then we go back. So we'll look at those same events here in the echo file at the end. And this is a new feature, the event ID. The one that has the ID of 100 is watching the stop sign. So is it is our closest object a sign? And if it is it a stop sign? Or is it a speed sign? Or is it a red light? Or is it a yellow light? Then we have another group here with ID 110, and that's our bike lane. Is that if this is not 0, then we would do something, and this can go back and forth. Now, if you've used events, you know that you will sometimes want to just reset them all. And that gets complicated if you have multiple subsystems in there, or if you're looking at different things, like we have the bike lane detection and we have the sign detection. So with these IDs, we can reset one group and leave the other intact. And that happens in this example. If you look at the log file, you'll see that there's some resets involving the sign detection, but this other sequence where it's looking for the bike position stays intact the whole time. Okay, go to the another example here showing a new feature. This is traffic signals, and we'll take a look at the existing one first, which is not what we ship. It's one that I modified. We have 3 lights up here. We're looking here at vehicles going south. The straight road is north-south. The Ego vehicle is coming from the east, driving west. There's a red light facing us and a green light facing south. You see the blue detection ray there. It's seeing both of them. Now that's not good. It's going to get real confused because we want it to only see the red one. And in past version, we put some invisible objects in there to block it, but we have a much cleaner solution now in 2019.0. We'll look at the traffic lights here. So this is the data set used for all 3 of the traffic lights. They're just located in different places. And so we've got where it's located using symbol stack things, so it's reusable. The type of shape is a cylinder. In all the past versions, you had 2 options, a cylinder or a rectangle. Now we have 2 more. The segment one is what we intend to be used for signs. And this has a limited visibility angle. If I say 40, that means that its whole field, kind of a field of view from the object side, from the target side, is 40 degrees. That's 20 degrees on each side. So if you are facing the stop sign, you can see it. If you're within 20 degrees of facing it, you can see it. If you're more than that, you can't. And I said stop sign, I should have said traffic light. So if you're within 20 degrees of facing the traffic light, you can see it. Otherwise, you don't. So we'll redo that run. Look at the video. Now we don't see the green ones because we're more than 20 degrees away, but we do see the red ones. Now you notice that those traffic vehicles are slowing down pretty realistically there. That's another big improvement we made with this release. We also see that the traffic vehicles following this is our blue Ego vehicle, that they slow down, and then when it speeds up because the light is turned green, they follow it well. Also, look at where the rear wheels are. When our driver model tries to follow the dashed blue line there, that it keeps the center of the front suspension pretty much on that line, and the rear wheels track inboard due to off tracking. The rear wheels are trying to follow where the front wheels are. And that just comes from the physics of the vehicle dynamics. These other vehicles don't have full-blown vehicle dynamics. This is not a CarSim model. This is a moving object. But it's tracking realistically. The front wheels are following the dashed blue line. The rear wheels are tracking inboard. So let's take a look at how that's done. I've got traffic vehicles here following the Ego. Here's the one right behind it. Now in the past, we've had 6 options here for controlling it. The first 3 control position explicitly. That way, and that's all we had maybe 5 years ago. It had no true degrees of freedom. It just went where you told it to go. So we could put a formula for station, like be some variable distance behind the Ego vehicle. But the only way you would get speed, it would be by doing a finite difference. Then we made speed a built-in variable, and if I choose one of these, it adds a degree of freedom. So now we would be controlling the speed, and then the solver would numerically integrate that speed to get the position. And now with our new one, we've added another option, that we will control the acceleration. That becomes a degree of freedom. And that's what we're doing up here. This is a term it's in the documentation, a speed error, that the built-in controller is going to change the acceleration to try to maintain a following distance that's speed dependent on what's in front of it. So when we do that, we have a degree of freedom for the acceleration. That's numerically integrated to give us the speed. That's numerically integrated to give us the position. So that's 2 degrees of freedom. And then within the last year, we had added this off-tracking option. We revised that a little bit with this release to make it more robust. That is adding a differential equation for the yaw angle. So the yaw angle is now the yaw rate is integrated to give the angle, and that gives us the realistic off-tracking that we saw. When we do the caravan, it's real simple. We just have each one is following the guy in front using the same control law. The cycling that we have for the light is real easily changed. A whole cycle is normalized to be 1. I had it at 0.7. I'll change it to 0.4 and rerun it. So here we have some speeds. The control for our lead vehicle here was smart enough to know that it has to come to a stop if it's a red light, and it can keep going if it's a green light. Because it's acceleration control, if the thing switches, it doesn't have a discontinuity. It maintains continuity by staying within reasonable acceleration limits. And now we have the red light over here. These guys stop in a physically believable manner. And then when it changes to red, they all accelerate to follow it. So that's 2 examples that we have, and I've got 2 more. A request that we've had for quite a while, especially from Japan, is to be able to have walls to the side of the vehicle. So here is an example. So we see that we have our Ego vehicle here that's blue, a motorcycle that's red, a white vehicle, a wall, and an access road over here with a dump truck, I think. The ray that goes from a sensor that's kind of where the rear view mirror is here to see the wall, it's blocked by the white vehicle, so we've got the occlusion going on there. And now we get to a point where the wall is no longer blocking the view of the truck here, so we can see that. And you notice that the wall is curved a little bit to follow the road. And as we go further, there's another wall, and this has a more dramatic curvature. Now, how do we do that? We'll look at the procedure here, go to the lanes. In addition to the cylinder, rectangle, and segment, we now have the option of having a polygonal shape. And we say polygonal instead of polygon because it's not necessarily a closed polygon. It's defined with a set of coordinates. You can choose S and L to follow a path, or X and Y. In this case, when we look at the S and L, they're very simple. It's just 5-meter intervals in station, and they all have the same lateral offset there. But it's because this thing is tied to the specific path and road that we're on, it gets the curvature properly. Now I have one more. We'll take a look at this first from looking at the data. We will go to the a building here. In this case, we're not using SL coordinates. We're specifying its location with X and Y coordinates. The polygonal type is X and Y. And this actually is a polygon. It's just describing a irregularly shaped building. Now we have also in here a bus that is using X and Y coordinates. And this is mainly here to show that we can handle an arbitrary shape. I wouldn't say this is the best way to do a bus, but it shows it can be done, that we're not really limited. We can have a lot of points. The shape can be really irregular. We'll go up and see what this looks like. Looks like this. The green around here is what the internal model thinks that the target is shaped like. The stuff, the building with the textures is just eye candy. Now, as we go through here, we see that there's a vector connecting the column. It's seeing the correct traffic light. Now we get some pedestrians. It can't see the pedestrians because they're out of view of the building. But now it does see them. If we had a rectangular building, the corner might have blocked them, but it's irregular, so it's got a clear view of the pedestrians. One goes to the crosswalk, one comes towards us, and over there in the background is the moving irregular object that is a bus. Those three examples, or four examples that I showed, are using our built-in target objects that may move, may not move, can move or be stationary, with controls for handling them, and our built-in sensor that is using just 3D geometry to calculate a vector to from the sensor location to the closest point on the object, and then about 20 other variables that you might be interested in. A completely different way of doing this is to use the visualizer. Now our visualizer is showing a full 3D world. It has things that are transparent. It has the walking pedestrians with their arms moving, gaps between the legs. If you have a big truck and a sports car on the other side, you can see the car underneath the truck. We can have multiple cameras, so we can have as many views of these as we want. And the feature we put in a couple of years ago is an API so that you can share those camera views with other software. And what we're looking at on the right side here, the left image is Visualizer. The right image is coming from Simulink. Down here on the bottom, you see an icon that has the picture, the CarSim icon on it. It says Live Video. That's our vehicle dynamics. There's another one here on the left, and that's a plugin for Simulink that interfaces this camera view with Simulink's signals in Simulink, and you can use the image processing toolkit in Simulink to do calculations. What we're sharing is an array of everything that you see in the camera with, for each pixel, RGB values, red, green, blue, distance, and a vector normal. And you can access this with several kinds of tools. This is a pedestrian. When we play it, we see the icons down here. The animator sets up. We run this under the control of Simulink. It's a little bit slower than real time, but not much. And now this is all Simulink showing us what we're seeing here. The identification of the pedestrian is with the Simulink library routines. We look at again, moving. So left is the visualizer, right is the pedestrian. There's a rudimentary control in here to not hit the pedestrian in this Simulink model. Now, a neat example that we've added in the 19.0 release is to do this without Simulink using Python. So in this case, the visualizer is providing a camera running the same example I showed earlier with the bikes and the pedestrians, but instead of having our built-in simple sensor model, it's got code in Python that is processing this. So now go ahead and make the run. It just generates the things, the files, starts our visualizer. Then you go into a Python environment, give commands to start the run. We're running CarSim from Python, and it's making use of a library called TensorFlow from Google that's open source. So this identification is not done by us, mechanical simulation. It's done by TensorFlow an example from us.
Like that example is available on the website.
Yeah, and Jeremy's keeping me honest here. That example, because it involves open source stuff, we don't have it in our installation, but we have it on our website. So you can download the example and you have to install Python and TensorFlow yourself, but then you can run that. Okay, the next thing I wanted to talk about is how we're getting these scenes built. The ones I've shown you so far were made using the standard road building tools in our products. But there's been a lot of interest in being able to make more complicated intersections and road geometries and represent things that are in the real world. So a year ago, we added an interface to our GUI and browser called the Scene External Import Screen that can bring other data in and get it into CarSim or TruckSim or BikeSim. The first tool that we had is called the Atlas web page that's on CarSim website. It gives you access to Google and Here mapping services. Now here's an example that has been speeded up and edited so I can show it in a few minutes, where we take a real intersection outside of Ann Arbor from I-94 to Jackson Road. We find it over here. This is Google Map showing us what the intersection is like. Now we'll go into Atlas and zoom in and find that same intersection in Atlas. We're using Google Map here, and Google is wanting to give us directions, so we use the interface of having a green start point and a red end point. But instead of getting directions, we click a button that says download, and it's grabbing GPS and altitude data that we can import using that screen. Now it's also giving us a reference point where 000 in our XYZ coordinate system is. We add some animation real quickly to get the bare minimum, and this is what we just downloaded. Okay, now we want to do the whole exit here, so we'll move the endpoint, force it to take the exit, download that, import it. The box is unchecked to generate a reference, so this is going to use the same GPS coordinate system that we had previously. So the XYZ coordinates from this should match the coordinate system from the previous one. And we'll make one more here showing the local road. This is Jackson Road. We can adjust those points as we need. Download that. Bring it in. Add some animation effects, and now we'll see the three sections, and we hope that they're all connected properly. We run the simulations just so we can view it. Now we see that they are located correct if you were looking from above, but the Z coordinates need something to leave something to be desired. We have editors in here, so we can see that the problem here is that where I-94 went over Jackson Road, Google gave us this altitude for the local road instead of the overpass. So the quickest fix is to just take out the bad data points, which we do here. And then we can also improve it by using built-in filtering options. So we'll do some smoothing in here to get the interstate to get rid of some of the noise that comes from importing GPS data. For the local road, you see there's a little bend at the end there that we don't like. I think it goes into someone's driveway, so we'll take those points out. That looks better. We do the same thing with the exit. Now we have the three roads that have been cleaned up a little bit. Still not much in the animation sophistication, but this looks very good. We can use these for realistic simulations. It's pretty easy to add animation assets using our built-in. There's a wall separating the lanes on the expressway. We've got grass on the side. Double yellow line on Jackson Road, the right number of lanes. And then if we take our assets that are in here like crash barriers and use variable width roads, we get the exit that starts out as a single lane. It widens to 2 lanes. You can only make a left turn or a right turn. There's paint on the road that's built in that we can you can select from those. It changes from asphalt to concrete, back to asphalt. We've got the overpass and the ground under it, kind of showing what it looks like. So this was provided in 18.1 with a 33-page memo, We've improved the interface a lot, so it takes much less time to do this with 19.0. You start out with something that you find from Google Map or another viewing service, go into Atlas, and end up with something that's in CarSim, TruckSim, or BikeSim. So Atlas is one tool. Uh, the other service that we support is here, and besides using Atlas to get access to here data, they have an 8SRP database that they provide. If you have it, we have a plugin that works with that. We have a scene builder tool that we added a year ago that I want to show next, and this is the direction that we're going for making complicated scenarios real quickly. We'll go and show this. It has tiles that are in here. It's strictly drag and drop. You move them over. You can make as many copies of it as you want. You can rotate them. You make paths very easily by connecting the dots, where the dots look like little arrows here. So we go marching along. I've made a new path here, and I can get SL coordinates or XY coordinates just by moving a cursor over there. I'll write down the X and Y coordinates where I want to put some a stop sign and some people. So this is kind of abstract, and now you see that when we do a video preview, this is an urban environment that's pretty complicated. These are the X and Y coordinates where I want to locate a stop sign. These are S and L locations for locating a pedestrian. And so this is what we end up with. This is real similar to what we saw earlier with the walking pedestrians and the bikes, except we've got the nice detailed urban environment here. When we introduced the scene builder, we provided documentation, so if you have artists on staff, you can make your own custom assets. And with 19.0, we've added compatibility with OpenDRIVE files. I'm going to show how you do that real quickly. Miscellaneous OpenDRIVE. Go up here and do scene builder. So this is a live thing. We have tiles for highway, rural, transitions, standalone. This is M-City. If you want to get M-City in here and want to build paths, we've got hundreds of points here to connect paths and make them easy. How do I get rid of that? We've got our animated things, our environment things, signs. We'll go back up here to OpenDRIVE, drag it in here, and I'll add a path in OpenDRIVE. We'll start here. It's a very confused path, but you'll get the point. I'll stop it, call it Mike. I've got to export it. Ah, there we go. Okay, so here's the one that I just imported. Run it. And view it. And so here we are. We've got the lines and the textures. I know I'm running late, so we'll go kind of see the whole thing in there. So we do support importing OpenDRIVE now and getting complicated things from there pretty simply. Now the last thing I want to talk about is how we interface with other graphic engines besides Visualizer. Visualizer is what you get with any of our products. It supports hardware in the loop. We have full-featured plotting capabilities, but it's to complement our stuff. We don't have any 3D editing or motion editing in it, or 3D ground. You get that from the CarSim, TruckSim tools. It has basic lighting effects, but the good thing is it's automatic. It's the easiest thing to use there is. Another one that we're being used with is RF Pro. That's it's a graphic engine targeted for automotive engineers. It's a derivative of a video game called R Factor that was developed in Ann Arbor by Jeremy here and some of our software development guys. So we're familiar with that. It's the professional version is a UK business, and they mainly provide fairly detailed databases for racetracks, test facilities, urban centers. They're very good. They're also very expensive. The animation quality is similar to ours. It's a little bit better. They have day, night, and rain. It's kind of a turnkey solution. If they make a database for you, you can run it, and it's ready to go. If you want to make changes, you might have to hire them to do the changes. Now the other two up here are Unity and Unreal, and these are not designed for automotive applications. They're designed for game developers. So people who are making video games, first shooters and driving simulators might have Unity or Unreal doing their engines. So they don't have any kind of a plotting support, but they have lots of editing and creation support. They also have better lighting, support day and night, multiple light sources, rain, fog. Unity has been used with our stuff in driving simulators. Unreal has been used for driving simulators. We've tested it with VR headsets, and there are some interfaces that use camera sensors similar to what I showed with Visualizer. Now there is one complication. These graphic engines like Unreal are top-level programs. It doesn't plug. You can't plug it into Simulink. And Simulink does plug into MATLAB, but MATLAB doesn't plug into anything. So you can run Simulink as a high-level program, or you can run Unreal as a high-level program, but neither one of them can plug in. So if they're going to work together, it has to be through co-simulation using TCP/IP or UDP to communicate between them. CarSim can plug into either one. Plug into Simulink, you've seen that many times. That's over here on the right, method 2. And then we have to have something else that plugs into Unreal. Or over here on the left, we can have CarSim plug into Unreal, and then we have to have something else that plugs into Simulink. Well, the something else is called VS Connect, and that manages the communication. I'll show in the next slide here is method 1. We will run with CarSim plugging into Unreal. Now the nice thing about when it's plugged in, we have a very fast communication rate. So we'll be getting information from the ground at a kilohertz. So the tires are getting really updated information. Simulink is only communicating when there's a frame refresh, which is about 60 hertz. We're doing a simple ADAS, or a simple adaptive cruise control here. So the blue car is following the red car. The controller is getting updates at 60 hertz, which is enough to do that. The tires are getting updates from the ground at 1000 hertz. So this is our method of getting Simulink and Unreal working together. Now after we showed that, some of you with trucks said, how do I do TruckSim with this? And is there a faster way can I have the vehicle model communicate with Simulink faster and Unreal faster? So we've completely redone it for 19.0. Instead of having the CarSim plugin, it's now the Vehicle Sim Dynamics plugin. It includes three parts: CarSim, the complete CarSim model and all the things that CarSim supports, TruckSim and all the models it supports, and VS Connect. We've also changed the architecture, the way we communicate with the ground, with a new API called VS Terrain API. And it's being generic here. It can get high frequency input regardless of where the vehicle model is, and we don't care how many tires there are. So that lets us support TruckSim and CarSim with trailers. Here's an example, and I asked them to make an example that was something we couldn't do with Visualizer. So it's a real dramatic lighting here, big shadows, it's got reflections, and the thing that we want to look at is the tires, that when we go on an uneven surface, they're behaving just as they would in any other truck simulation. There's no unwanted craziness or vibration. So this ground is all created in Unreal. The TruckSim is the same TruckSim that you would be using at any time. Okay,